bindless resources, and GPU-accelerated ray tracing. To address any issues, we also need to collect data from our players' hardware so that we can use that to target specific features and extensions. We're not aware of any large-scale multiplayer games that captures Vulkan data live in the exact same way we do. Capturing this data allows us to plan ahead for any optimizations and then leverage that for the larger majority of players so we can bring you the latest and greatest. On screen at the moment is a diagram that shows the distribution available for Vulkan API versions amongst currently active players. This was captured in the last 3 months, and as can be seen, there is 98% of players that are able to use Vulkan fully in 1.2. We did see a negligible amount of 1.0 and some that were unavailable. We are actively looking into these cases, especially those that cannot currently run Vulkan as it is seen as unavailable.
I'd like to take this opportunity to also say, please update your drivers, as we do see a few cases where this can take you straight to the latest version.
I'd like to now explain a bit more about the render graph and how this works hand in hand with the Vulkan API in order to improve our usage of Vulkan. So a render graph can be seen as a collection of stages that depend on each other. This then determines the ordering, the scheduling, and the flow of the actual frame. This allows us also to then achieve any synchronization that we need to during that frame. It also helps us from a design point of view, as we can look at the render graph and see where there may be issues or potential optimizations. The render graph also allows us to keep track of any state of resources, and we can also validate against those resources as well. Now I would like to explain the render graph as a whole and give you an overview of how it works between the GPU and also how it works in terms of our frame.
So a frame is made up of a collection of passes, and sometimes we require a texture to switch states, perhaps between read and write. The graphics driver used to do this for us, but now with modern APIs such as Vulkan, we need to carry out this work ourselves. What the render graph will then do is insert a pipeline barrier into the render graph and pass this work along to the GPU and switch the state. We can also cache the render graph and use any data we had from a previous frame or perhaps similar resources as an optimization. I'd now like to talk a bit about the synchronization that happens within the render graph and how resources change state. So the idea is that we want to switch the state of a resource as early as possible. We need to then also validate that this resource is in the correct state. So from the diagram, we can see that the depth prepass writes to image A, but then later on we require to read from image A in the G buffer. So to this end, we insert a pipeline barrier for this transition between the two passes. These barriers are scheduled as GPU work, following a strict ordering dependent on other work that may have happened previously.
All the work for a single stage within the frame can be carried out in a single pipeline barrier. I'd now like to talk about some of the more nuanced areas of our Vulkan implementation and how this affects us as developers and you as players. We use the Directx Compiler for our shaders, and this can compile our HLSL code into SPEAR-V. DXC is a more modern compiler and has features that span both the D3D set of APIs and Vulkan. HLSL is a shader programming language that we as developers can utilize and read in order to make work happen on your GPU. This HLSL is compiled down then into SPEAR-V. SPEAR-V itself is not as readable, as it is seen as an intermediate language between HLSL and shader microcode. SpearV gives us less driver overhead at compile time. We can use this then to create our shader modules in Vulkan and optimize any dead code away. DXC also gives us Shader Model 6. Shader models have progressed over time in HLSL, with Shader Model 6 now giving language support for GPU parallelism, as well as variable rate shading, amongst many other features. We can see here now a diagram of how our shader compilation happens. It starts at the shader author level. This is where one of our many developers will write a shader using HLSL code with some markup integrated into that HLSL. This HLSL is then passed to the preprocessor. The preprocessor then removes any of the additional code that we don't need and is dealt with accordingly, whilst then outputting just HLSL code. The HLSL code is then passed to DXC, and DXC will change this into SpearV. It's at this stage that we can carry out any additional compiler optimizations and improve compile time performance even more. SpearV is then passed to the driver, and the driver will then change this into microcode, which will run specifically on your GPU hardware. As I've previously mentioned, there have been several Vulkan core versions over time. Each one has added new features and extensions for us to reach into and develop with. Two of these I'd like to explain a bit more in detail now that we would like to look into and develop for in the future. These are both bindless resourcing and also fragment shading rate. Fragment shading rate can be seen as the same as variable rate shading, as you may have already seen. What this does is works on groups of pixels instead of a singular pixel at a time within the shader. This allows less overhead in the frame, whilst at the same time allowing variable amounts of these groups, including variable sizes, in order to have less fidelity where may not be as important to look at. Bindless resourcing is where we can take large groups of textures, for example, and reach in and grab one of these inside the group. This gets rid of the overhead of specifically binding two slots within the shader. This also extends to other resources, including buffers. I'd now like to talk a bit about the video RAM involved in your graphics card. VRAM used to be managed by your graphics driver, but with Vulkan and other modern APIs, this is now managed by the developers. There are existing solutions towards this. However, we have decided to use our own implementation. This is because we know exactly what resources are used upfront and how much memory these resources use. Using this, we can potentially beat what the graphics driver used to be capable of. As we know all of our resource life cycles, we can take advantage of that. From the diagram, we can see memory being paged in and out as it used to be when it was managed by the graphics driver. On the other side, we can see memory being allocated and then suballocated, and we can then offset into the data from this suballocation. The memory paging of years past could potentially result in a performance loss, because this was seen as a more one-size-fits-all. We, of course, want to avoid any of that performance loss and the memory cost involved by offsetting into these larger buffers. This can also help mitigate cache misses. This then leaves us with all of the allocation, freeing, usage, and reusage of resources. I'd now like to pass you back to Alistair Brown, the Director of Graphics Engineering.
Following on from what Dowell explained there with the explicit memory management in Vulkan, we're intending to expose some of this memory management to the player through the advanced graphics options. We're going to let you tweak the memory assigned to each system so you can balance the preferred visuals and performance for your experience. For example, you may want to balance the output resolution of your game to a higher resolution, but then sacrifice some shadow quality. Or maybe you want to use a lower internal resolution and rely on upsampling to achieve higher texture quality. These options will all be available to you, and obviously only capped by the hardware that you possess. So to summarize, with our Gen 12 renderer, we're hoping to achieve something that is more efficient, modular, flexible, and minimal abstraction to the hardware, and uses modern graphics APIs like Vulkan. So now you know a bit more about what Gen 12 is, I'll try and let you know where we're up to. So we've done a huge amount of work already. The architecture is all in place, and we're using this hybrid rendering approach where we're combining elements of the old and new render at the same time to allow us to move piecemeal to the new system. All of the post effects, fog, and lighting have been converted over, and they're all enabled by default in 3.15. And the fundamentals of scene and geometry rendering are all in place, but they're still being worked on. So our main focus is finishing that off at the moment, and once that's done, our focus will shift to the remaining major systems, which are gas clouds, the render-to-texture system, and a few special cases for transparency. After this, that's where we'll start seeing the public milestones, and the first of that will be 100% usage of Gen 12 and none of the hybrid approach. This will still be at DirectX 11, our current graphics API at this point. And then our second milestone will be the Vulkan API release. That will be optional at first and then mandatory after we've removed all the bugs. And then a final milestone will be when we have performed the optimizations for multi-threaded. So that will only happen once the Vulkan is in place and we can finally look at the performance on the final graphics API and optimize all the remaining code. So after Gen 12, I just briefly wanted to touch on what comes next for the graphics team. So a lot of Gen 12 has been focused on CPU performance. So after Gen 12, we really want to start looking at the GPU performance. The first few things we'd look at here were things that wouldn't change the visuals, just improve the frame rate. Things like DLSS, FSR, async compute, and variable rate shading. After we've improved this GPU performance, we want to start looking at some of the more exciting visual features. So then there is also mesh shaders and primitive shaders, which is technology we can use to generate procedural geometry. And this type of thing could be really exciting for things like the planets or asteroid fields where procedural geometry is critical. And then there's the big one, ray tracing. We're very excited to get onto ray tracing, especially to use it for lighting, such as global illumination, but also reflections and shadow quality. There's a lot of exciting areas for us to look into, and we can't wait to get into it. So that's it. I just wanted to say a big thanks to everyone that's been involved in this technology. It's involved the graphics team, engine team, VFX, and Planetech all working together on a huge piece of code. And we can't wait to get into your hands as soon as possible.
Shadow. Nowhere else to run.
Paladonians. I heard stories about you lot. Bounty hunting, piracy, assassins. You're the scum of the verse, they say. No job's too dirty.
Is that all you've heard about us?
No. You have a code. Which means I ain't talking my way out of this, am I?
This is the way.
Are you traveling the stars? Exploring the galaxy? That's lonely, lonely, hungry work. Always remember though, Big Benny's with you. Big Benny always has your back. Big Benny, eat his food.
Rabbit! The dude really said, update your drivers. These are my favorite kind of panels because they're precisely the kind of thing no other game studio would ever dream of sharing with folks. And as CitizenCon 2951 rolls along, there was a lot to take in there, wasn't there? I know server meshing and the like are the big buzzwords, but there are a lot of performance improvements to be gained throughout the teams on Star Citizen. And for graphics, they're not only moving to Gen 12 and the faster and more flexible renderer that it brings, they're also focused on re-engineering for multi-core systems to provide improved CPU performance and remove some of our worst bottlenecks. And that all of this work starts with DirectX 11, but will transition into Vulkan once things are ready. Now, the work of these folks, the meshing folks, the database folks, the optimization folks, and countless other folks, I've used that word a lot, from teams across every studio is how we're going to get Star Citizen to that performance promised land. And it takes all these teams to make that dream a reality. And speaking of dreams made reality, hey, Sleepless in Stanton folks, don't think I forgot about you. Don't think because you're a community effort, I can't expect and demand a full-length feature. I await my screener. And in other community news, one of the best things to come out of the Star Citizen community over the years has been the creation of an app called Game Glass. It's an app that turns your tablet or phone into a control surface for the game. So let's take a closer look at that now. Now up next, we've got Anise, Mark, Morgan, Will, and Marco taking a look at some of the new tools currently in development, including Rastar, which you may have seen a little bit of in the Pyro presentation. Crafting Worlds, Planetary Tech and Tools starts now.
Hello, I am Marco Corbetta, VP of Technology, and we're going to talk about some new Planetary features today. First, Anise is going to give us an introduction about Gen 12 and what that means for planets. Then Will is going to talk about dynamic foliage, shaders, plants and seasons, and he's going to show us a river demo as well. Then Mark and Morgan are going to talk about Rasta, our new base building tool. So let's get started with Anis.
Hi, my name is Anis and I'm Senior Engine Programmer here in Cloud Imperium Games. My main responsibility is the development of Star Citizen planetary technology, with a focus on planetary elements rendering. While there is another talk dedicated to Gen 12, I wanted to touch a little bit on how it applies specifically to Planet Tech. It's our rendering abstraction layer API. It aims to provide next-generation features for our 3D engine by reducing some CPU latency and rendering comment submission overhead, which is a significant bottleneck for our game. Part of our recent efforts have been put to modernize our old-school renderer to shape it in a conformant modern API rendering style, to be suitable for the newest low overhead APIs, such as Vulkan. Today, I'm going to talk a bit about Gen 12 benefits for planetary rendering features. As I said, Gen 12 key aspect is performance. The way this is achieved is to make comment submission easier for multi-core CPUs. All Gen's rendering APIs rely on a single thread, in which you have the view of a single timeline where GPU comments are guaranteed to be executed in order. The driver does the rest and is responsible to handle memory and synchronization. Gen 12 can scale much better, thanks to the ability to dispatch in parallel comments that are submitted from different execution units. The memory is directly handled by the renderer, and synchronization primitives are used to make sure comments dispatched in the right order by considering cross-dependencies between resources. Since the rendering driver is thinner and more responsibility is given to game developers, this opens a new opportunity to forge a new renderer for specific needs a game like Star Citizen might have. Our planetary technology introduced a new set of engineering challenges, so we need to be very creative due to the fact that most game industry standards techniques are not working very well for Star Citizen. Thanks to Gen 12 optimizations, we can push our planetary rendering computational budgets to perform more GPU operations. This translates to better visuals, more details, and less compromises. As a member of the Planet Tech team, I will show you some improvements we've recently made for our Planetary Terrain rendering pipeline. We made two important terrain improvements. The first is at ground scale level, and the second is for large-scale purpose. Both techniques use dynamic tessellation. Dynamic tessellation is a GPU feature, which allows to increase the triangle count on the fly, before a sterilization stage occurs. The new triangles are then manipulated to shape the terrain high-frequency details and improve surface visuals. This new technique is replacing our parallax relief mapping, which is a per-pixel technique. And instead of creating geometric details like tessellation does, it works by simulating details after the rasterization stage, with a cheaper approach by tracing rays from camera to surface. The second improvement targets planet visuals at long distance. This technique is also tessellation-driven, and it aims to improve terrain-ocean intersection, where CPU geometric representation lacks for enough control points in the geometry. We've reached the conclusion. Thank you very much and enjoy the rest of CitizenCon.
Thanks, Anis. I'm Will Hayne and I work on the Planet Tech team. Over the past few months, I've been working on a number of improvements to our ecosystem spawning system, which is the system that spawns all of the objects on all of the planets. We've been doing this to give our artists more power and flexibility, as well as improve performance for everyone playing the game. The first thing that I did was a complete overhaul of how we spawn the objects. We used to spawn them on each terrain patch as that terrain patch was created, but this meant that we were limited in our control in that we could only spawn new objects when we were creating new terrain patches. The new system has an entirely separate grid division of the planet, and this means that we have a lot more control over the resolution of our objects when they're spawned and how we spread it across multiple frames, which means that we get better performance in the client. This also means that we're able to add a setting for the clients to control how far away each object preset was spawned. The next improvement we've started to look at is making the ecosystems react to their situation and surroundings more. For example, we can now introduce scaling biases for temperature and humidity so that certain objects, when in higher humidity can be bigger or smaller, and the same for temperature. A new system has been designed for animal and entity spawning using tokens, which means that we can specialize our object presets better for different planets. For example, we have something similar for rocks. That means if you put a rock on a snowy planet, it goes snowy, and if you put it on a sandy planet, it looks sandy. Now we can do something similar for animals. We can specify a small herbivore, for example, and in the snow, this might spawn some sort of Arctic rabbit, and in the jungle, this might spawn something completely different. We've also begun to experiment with a new foliage shader that takes into account the health of the plant based on its surroundings again, and the current season of the planet, though what you're seeing on the screen is far from final. In the same vein as that, we've been working towards having more dynamically placed biomes around natural areas. We've created dressing object presets that are automatically placed around coasts, and of course my favorite thing to work on, rivers. In the most recent couple months, I've been doing more work on the rivers to prepare them to be closer to what we consider shippable, so that we can get them out to the players. This has included finer control of both the shape of our rivers as they flow from springs to larger rivers, but also the objects that spawn around our rivers, so we have control over what spawns in the water, what is spawning on the banks of the river, and what is spawning further away and blending it into the biome that it flows through. The other thing that we've added as well is a wet edge around rocks, both in the sea and in rivers, which reflects the fact that they were probably wet from the river, and so they look a lot more shiny. We've also been working on introducing basins to the river system so that we can have more natural pauses in our river systems and other bodies of water than just the oceans. Another major change was to stop using the planet's ocean mesh and just displacing it up to the river, and instead building specific river mesh sections around the river. This means that we can have far more control over the shape of the water, and we can use our own specific river material and shader, meaning that we can specify colors, flow, and other properties of the river water separately to the ocean of that planet. Rivers aren't done yet, but they're closer to being used in production than ever before. The next steps include a planet populating tool, so one click to create an entire river system across a planet, and maybe working on a little bit of lava flow, but we'll have to see when that comes. Next is Mark and Morgan. Thanks, everyone.
Hi, I'm Morgan. I'm a tools programmer from the Planet Tech team, and now I'm going to talk about Rasta. What is Rasta? Rasta is our work-in-progress tool for planetary locations creation and edition. The name stands for a mix of RTS, the game jaw, which takes the inspiration from its map editor system, and Sta, as well you know. Its goals are to replace our previous placement system based on prefabs to a better object container-oriented solution. As our previous system was based on prefabs, any changes to location was source of issue, as it needs to re-enable a whole set of data to have things like missions or shops to work again. With this new system, any change will be easily manageable and won't require us to redo work when a change is made. Plus, as it's now object container oriented, it can be used for outposts, caves, or even derelicts, and more. It works as a modular system where locations will in fact be made of small elements that will be placed just like you do in City Builder RTS editor. And in a matter of minutes, we now have a new location where we can now create a bunch of cool gameplay. Let's go to Mark, who will tell us about the connector system.
Thanks, Morgan. So, I'm Mark. I'm also a tools developer for the Planet Tech team. Do you know what's better than placing everything by hand? Not placing everything by hand. In order to do that, we use what we call connectors. Basically, artists create small parts of homesteads that we can then snap together. Every part is modular, so we can interchange multiple ones in order to have procedural homesteads. Every change is very simple. We can change like the whole inside of a homestead, or only a building that is a part of the homestead. In that way, it's very easy to make a lot of different buildings. Once something is connected, it is considered a part of the whole. So it moves as one, it can be deleted and changed, and it's basically all for connectors. So back to you, Morgan.
And last but not least, some of you might have noticed that the UI is not looking quite like an engine UI. And that's normal, as it's based on our in-game UI tech building blocks, and that for a reason. While today it's being used by our developers, one day, when it's ready and been thoroughly tested internally, we'll make a version available to you, the player. And Rasta is what will make you a pioneer. Thank you for watching. We are very excited about the tech we've shown you today, and we hope you enjoy the rest of Digital CitizenCon.
So that was a small sample of what our team is working on. I hope you have enjoyed it. Enjoy the rest of CitizenCon, and thanks for watching.
No, it's not me. It's time for...
Push up! Moving! I got you covered. Pushing. Got visual on the bridge door.
We're going in.
Get down on the ground!
Hands where we can see them.
No sudden moves! What is this?
It's a goddamn failure, that's what it is. Command, the target is gone. We've been stitched up.
Blast it. The hub's still on. When we catch this bastard, he will run out of luck eventually.
Are you tired of that same old commuter train? Feel like you're just one in the crowd? Was that burrito the best thing about your day? Out on the frontier, there are opportunities aplenty if you know where to look, and if you've got somebody to help you find them. Somebody to pick you up when you're down. Somebody to watch your back out there in the black. We're recruiting across our industrial, security, exploration, and merchant divisions, so if you think you've got what it takes to make it on the frontier, think Frontier Consolidated.
It started in Port Olisar.
The first case was 6 years ago. Nobody knows what happened. He just dropped dead.
Now it's spread through the Stanton system.
I've seen it hundreds of times. Last words are backspace.
Backspace. We followed an elite team of researchers in a race to contain it.
Why can't I recreate it? I just don't know what we're missing.
Professor, there's a new case nearby. We need to check it out.
Can they stop it in time?
Are you struggling with your career out in the verse? We
We are too, but we're here to help. The Garden Interstellar Initiative. The Garden Interstellar does not guarantee fruits and vegetables will be available for all and cannot be held accountable for the lack thereof.
I feel a little called out by both Project Black Space and Garden Interstellar. And hey, at least we all know what my surprised voice sounds like now. That was new. That was the Planet Tech panel, and the big news watching the chat was clearly Rasta, the beginnings of which will one day let players build their own outposts like the ones we've seen, and others still yet to come. But up next, the Cosplay Contest returned this year, and it's been open for a couple months now. So the community team narrowed it down to a couple finalists, and then their panel of judges have selected the winners. And I was not asked to judge this year. Why was I not asked to judge this year? It might be because they figured out I was buzzed on British cough syrup during the 2019 event. Could hardly tell. So let's take a look now at some of the finalists. All right, and the winners. Let's see what we have here. In third place, Calamity, who's worked to prove that it's not all about armors and weapons. Sometimes you just have to look good on the dance floor at Wally's bar. In second place, Diabolus, back again and always a force to be reckoned with, this time rocking Legacy Heavy Outlaw armor and a laser sword. You can't just add a laser sword, can you? And finally, in first place, it's OG Star Citizen Ken Shadow, who returns with a Grey Cat Errol armor, complete with backpack created through a combination of EVA foam, 3D printed PLA, and poured resin for the clear pieces. Now, true story, I once spent the day pushing Ken Shadow around Disneyland in a wheelchair, but he never actually explained to me what his injury was. It's possible I was taken advantage of. Now, congratulations to all the winners, but there's still a fan favorite award. You can head over to the website now and cast your vote. I forgot to ask what the prize was, so I have no idea what any of these people won, but I'm going to assume it's a 15-minute call with Tyler Wicken to ask all the when questions you could ever want. Congratulations, everyone. Up next, it's one folks have been waiting for. Paul Rendell and Benoit Beauséjour take us through the programming and engineering looking glass with server meshing in the state of persistence, starting meow.
The concept of server, which has been ingrained since the beginning, has changed to become a mesh of servers.
So how do we solve this? The answer should be simple. Hi, my name is Paul Reindl and I'm the Director for Online Technology here at CAG. I wanted to take this year's CitizenCon as an opportunity to give you some insight into our exciting persistent streaming and server meshing technology. In this talk, I will cover a quick overview of the current streaming and server architecture and how we plan to transform the existing tech into what we call persistent streaming and server meshing. I also have Benoit Beauséjour with me, who later in the talk will give you more insight into the graph database that is powering persistent streaming. Hey Ben, how's it going?
Hi, Paul. Hi, everybody. I'm super excited to share some of the details about what the game services team at Turbulent has been working on to support the efforts to build this technology and make it a reality for you guys.
Cool. Let's get started. Before we look into persistent streaming and server meshing and how this new technology will work, let's have a brief look at entity streaming and how our solar system is set up. Each solar system can be seen as one giant level, containing every single object inside the solar system. From the sun to the wind to a rock, Stanton is one large map. Since this is a lot of data, the setup is split up into a hierarchy of nested object containers, which can be streamed in and out individually. If you look at an abstract view of Stanton, it all starts with one solar system root object container. This object container contains the sun, the planets, and the moons around each planet. Each of those locations then has its own object container, and if you take a closer look at a moon, you will find the entities placed around the moon inside this object container. For example, a space station orbiting the moon. This setup keeps repeating. The space station could be set up via multiple rooms, each defined by its own object container. Additionally to the static hierarchy of object containers, there are also all the dynamic entities which bring the universe to life. NPCs, an interactive vending machine, and of course players and spaceships. Most of these entities are made of a hierarchy as well. For example, a player has his body, an undersuit, and armor attached to it, and they are all child entities of the player. The streaming system treats these mini hierarchies as streaming groups to make sure that an object like a spaceship is always streamed in as one unit. Loading the entirety of Stanton into memory and simulating every single entity would be very expensive, especially on the client, but also on a single server. That's why we developed entity bind culling and object container streaming, which allows us to stream object containers and streaming groups individually. When the game server starts, all entities and object containers within the solar system are loaded into local memory of that game server. These entities are not streamed in, we just store the initial state in server memory. When a player connects, we create a so-called streaming bubble around that player, and object containers as well as streaming groups that are visible from the player's point of view are considered inside this bubble. Any object container that is inside the bubble will stream its content, and any streaming group within the bubble will also be streamed in on the server and then replicated to the client. Entities are considered inside the streaming bubble if their projected screen size on a virtual 1080p plane is larger than 5 pixels based on distance to the player. So while a large object like a moon will be considered inside the bubble from far away, a small object like a ship will only be considered inside when it's much closer to the player. When the player starts moving across the universe, entities that leave the streaming bubble will become unbound, and the replication layer will remove these entities from the client. Entities that enter the streaming bubble will get bound to the client, which causes the network layer to replicate these entities to the client, effectively streaming them in. We call this technique entity bind culling because streaming on the client is driven by the network layer, binding and unbinding entities. If entities are not in any client streaming bubble, so no players in their vicinity, these entities are also streamed out on the server. They go back into a dormant state where they are not simulated. This model works quite well on the client. However, it doesn't scale well on the server. While we do stream entities on the server with no players close to them, a poor distribution of players will cause the DGS to load most entities, and the more clients we try to match to a given game server, the likelihood of a player being at every single location increases. And that basically nullifies the benefit of server-side streaming. So how do we solve this? The answer should be simple. Allow multiple instances of the game server to work together so they can split up the work. Well, it's not quite that simple. Let's have a look at the current architecture. As of today, we have a traditional client-server architecture. One instance of a dedicated game server serves up to 50 clients. This is called instance, as the dedicated game server has its own instance view of the persistent universe. Once the server is full, we start a new server instance, which then serves additional 50 players. As we've seen before, when a DGS instance is created, it loads a unique version of the Stanton system into its local server's memory. Therefore, each dedicated game server instance has a unique copy of every single object that's part of Stanton. As these entities only exist in the memory of the game server when the instance is shut down, these entities are deleted. The goal of server meshing is to allow multiple DGS instances to work together and divide simulation costs between each server in the mesh. In the best case, we can scale this to infinity by adding more nodes to the mesh. As we saw earlier, each server node stores the state of entities locally. If we want to mesh these servers together, we need to find an efficient way to synchronize state between each server. With our current architecture, depending on the vision of the simulation and the overlap, this would require a lot of synchronization points between each node. It's an exponential problem, as in the worst case, each node would need to talk to each other node in the mesh, severely limiting our ability to scale it. To solve this issue, we are separating simulation and replication. Instead of just meshing multiple dedicated game servers together and have them synchronize state between each other, we are introducing a new layer called Replication Layer. The Replication Layer has two major functions. It holds the state of every entity in memory and replicates the state to clients, but also to server nodes. I said server nodes because in this setup, the traditional dedicated game server becomes a game server node. This server node connects to the replication layer, very similar to a client, and only a subset of entities are replicated to that server node. Replication to server nodes is controlled by the network bind culling algorithm that we saw earlier, and is driven by streaming bubbles, and it works very similar to how it works on clients. The server node has certain streaming bubbles assigned to it, which will cause the replication layer to replicate entities from these streaming bubbles to the server node. Contrary to a player's client, a server node has the additional responsibility to execute server-side authoritative code for those entities, controlling AI, doing damage calculations, etc., etc. The result of this simulation is then written back from the server node to the replication layer, and from there it is replicated to all connected clients and other server nodes. Since streaming bubbles can overlap, entities may be replicated to multiple server nodes, exactly the same way how they are currently replicated to multiple clients if players are at the same location. To avoid two server nodes trying to simulate the same entity, only one server node can have authority over any given entity. And only that server is allowed to write entity state back to the replication layer. This is usually the first server node who replicated the entity, and other server nodes will only run client code on those entities. Basically, you can see a game server node as a client with authority to write the result of its local simulation back to the replication layer. Authority can transfer between server nodes. For example, if an entity leaves the streaming bubble of the current authoritative server, it is then transferred to the next server node that has this entity currently streamed in. Further, authority can be transferred between server nodes on demand in order to load balance the mesh. Since we now mesh multiple server instances together to simulate a shared state of the universe, we no longer call this instance, but instead we call it shard. A shard is still a unique version of the universe, and we still have multiple shards running in parallel. However, the server mesh will lift our current hard limit of 50 players, and it will enable us to steadily increase the number of players we can support within one shard. It will take some time, and in our first version of server meshing, we will still have a very similar situation as we have today, with quite a few shards running in parallel. However, this technology is going to enable us to start scaling the universe to become a true MMO experience. There are some fundamental differences between a shard and an instance, and for this we need to take a closer look at the replication layer and talk a little bit about persistent streaming. Previously, the entity state was held entirely in memory on the dedicated game server. And besides some selected persistent player items, all that state would be lost when the server is shut down or crashed. The replication layer is fundamentally different, as the entire state of the universe is stored within a graph database. We call this entity graph, and it's an evolution of the original iCache. When we create a new shard, the initial entity state of the universe is seeded into this database. This happens offline before we let player join the shard. When the shard comes online, the replication mesh caches the state from the entity graph. As player connect to the shard and as we start to spin up new server nodes, simulation begins and alters the state of the universe. The replication layer does not only replicate these state changes to connect players and server nodes, it also replicates the state into the entity graph. Since the entity graph is a persistent database, the state of the shard is never lost, and even if the shard is shut down, the state persists and can be resumed at a later time. Benoit is going to show you some more technical details about the entity graph.
Thank you, Paul. Get ready for a deep dive into the entity graph persistence database. The entity graph is our approach to persisting the game world. This is fundamentally different to what is happening today in the game, where only items you own are actually stored. Our objective is to be able to save the state of the replication layer, which includes all entities in a given universe shard, in order to provide a truly persistent world, where actions you take as a player can influence environments in the game world permanently. The entity graph, as the name implies, stores game data as a graph. This representation is native for the game engine because it is how internally those data structures the game uses are addressed and manipulated. Using a graph also has several advantages. We're basically storing and retrieving from a gigantic indexed list of nodes and edges, and those edges between those nodes are optimized in a sharded database. But in order to properly explain the system, we must first view the game world as the game engine sees it. Game objects are constructed of several game entities linked together in hierarchical structure. You can picture this as a tree, which is a specialized kind of graph. This is how the game engine holds and simulates the elements on screen as it is running the simulation. In a server meshing world, this is also how replicants hold the entities in memory for each of their assigned territories. For example, a ship is made up of several entities that make up different parts of the entire playable vehicle. Each part is parented to another entity until the root of the ship is reached. Each of these entity nodes holds properties with regard to what the entity represents in the game. The class of object it is, the item type, its legal owner, orientation, and of course its very precise physical location within the game world. Each edge in our graph qualifies the relationship to the parent. In the case of a vehicle, our edges store properties that tell the system which port is being used to attach the entity into the parent and what kind of attachment it is. An item port attachment, a zone attachment, many others. In a constellation, for example, the different major sections of the hull are entity nodes with edges to the ship root. We call this small graph of item an aggregate because it is a whole movable unit. The ship root in this case is called the aggregate root because it sits at the top of a logical object. You can think of what you normally call an item as an aggregate, with the aggregate root being the actual item you are talking about. For example, a first-person weapon with attached scope, mag clips, and laser sights is a small hierarchy of entities. We distinguish the aggregate roots from other nodes by giving it a label. Labels allow us to distinguish and rapidly look up and find nodes of a specific type, either when we retrieve parts of the graph or when we look up specific nodes. Those labels exist to allow correct reversal of the graph data when we query for specific things in the game world. Other labels include streaming groups, universe root, star system root. This allows us to really look up and index those types. But the tree depth doesn't stop there. Additional information is required for a fully functional ship. The insides of each of those structural entities have to be fleshed out. Object containers are the building blocks of how space division is achieved, which aggregates and what part of the hierarchy they're in. In fact, most major areas of ships are represented as OC entities attached to ship root or another OC. The shape of this data actually takes in reality is driven by designers. Of course, then, each of those object containers also contain entity hierarchies as well, expanding to have the common static and dynamic entities you're used to playing with, like elevators, beds, guns, seats, gimbals, and others. In addition to object containers that make up the structure of the ship, other aggregates can also be attached within the hierarchy of our ship. For example, a rover parked in the cargo bay of our Connie will be attached as a sub-aggregate attached to your ship's cargo grid. Same goes for turrets, which are changeable and themselves expose item ports, allowing guns to be mounted. For each of those entity nodes, a snapshot document is also stored. This document contains all the runtime values, the game components attached to those entities. This data is the dynamic part of the model where game developers can persist variables on any entity in the game world according to the rules of the game component. For example, damage state and health data are stored within the snapshot document of those ship entities. storing and retrieving data in graph form really have some awesome properties. It's a native structure to the game engine, so it gets loaded rapidly. It's very simple and effective to serialize and transport because it's just a list of nodes and edges. There are optimized databases that we can use that allow us to fetch entities recursively in a traversal rapidly, and the dataset can be sharded across multiple database instances reliably. One key element here and one big advantage of having a graph data is also that we can reduce writes. So in order to reduce that, all the hierarchical changes that we need to do can be minimized. For example, if we want to detach mutation command will detach an entity from the hierarchy. In this case, a single edge must be erased, which is a very inexpensive operation. A nice side effect of this is also that it's the same operation whether we're detaching a single entity or an entire aggregate. In both cases, the single edge must be erased in order to perform the detach. Rolling away in your stowed rover, detaching a gun from a replacement or for a replacement, or selling a turret becomes really a cheap operation to persist. That is good because that happens very frequently. Compared to a columnar approach where index columns must be maintained for every write, linking all objects to the aggregate root, this is really a great performance improvement. The same properties apply with the attach command, which will only have to create a single edge when rejoining items to the hierarchy, be it via attachment or parking another vehicle on a docking hub. The attach and detach commands are two of the many semantic commands that the Entity Graph API proposes, allowing to express a mutation to the graph. Other examples of the different commands are create, possess, transfer, stack, unstack, change location, change snapshot, bury, stow, and unstow. One important change and addition that comes about with the entity graph is also how mutations are applied to the database. Each mutation is composed of multiple commands which are executed in sequence but committed transactionally to the database. They either succeed together or fail and roll back together. This ensures that the changes to the graph are always consistent and no lost writes or errors can cause data corruption. For example, a mutation consisting of detach, transfer, and an attach commands would succeed only if all three commands are applied successfully. The system retrieves a constant ordered streams of mutation from the replicant scribes that are part of the replication layer and are enqueued in durable queues to ensure that no message is lost even if the service is unavailable or paused. It's important to understand that the graph does not only cover your ships and items, but the entire game world is made of this way. Your ship is actually attached to the zone host location you travel in. Your playing character is attached to your ship seat when you are piloting it, just like planets are attached to their star system routes. The game world, though, must exist in persistence before it can be replicated and mutated. This is part of a process called seeding, where a new database is created by the replication layer. It is during that process that millions of entities are initially created in a sort of a big bang. At this stage, every object container, every minor or major entity from planets to doorknobs are inserted into the entity graph in their default state. That is, the state that the designers decided was the initial state of the world. This process goes down from the universe root to the star system root, and into the different areas and planets, into their landing zone, their buildings, their rooms, down to the smallest possible entity. There are multiple types of entities that are created during this process. First are unstreamable entities, which make up the skeleton of the universe. Those are entities you do not get to see, but are part of and always present on every worker node in the mesh. It is by looking up unstreamable entities that the game world is able to stream in the other types of entities into your client and into the server mesh. It is from those entities that others' entities bloom. Static entities make up the game world that you cannot interact with. Most map objects that make up buildings like the Hurston Tower, rooms and walls of hospitals, or the bar at G-Lock are all made up of static entities. And the last type is dynamic entities. These are entities that you as a player can manipulate. A bottle on a bar, a door in a level, a ship component, everything you interact with when you're playing the game. Of course, during seeding, all object containers are also seeded as part of this hierarchy and inform the shape of the loadable subgraphs. The seeding process takes a couple minutes to complete, Once created, this newly seeded database represents a full dimension of the universe and will now persist as it is modified by players. As you play the game and go about with your ship, your playing character entity moves from location to location, getting attached to new zones as you travel. Your player aggregate is itself part of the Jang graph, and your location and state are persisted by the replication layer scribes to the entity graph of your given territory. When you interact with dynamic objects and their properties change, the state of that entity will not persist until this instance of